The high-performance matrices, the polymer materials, the different types of polymer. So this graph summarizes basically on the left, let's say lower end polypropylene, polyamide, also known as nylon. Blue is the glass transition temperature at which it gets soft, and red is the processing temperature. So if we go to the right, we go to materials that are higher performance, but also higher cost. And if we look at automotive, there is a lot of work in automotive on the left, polypropylene, polyamide, a little bit of work in PPS and PEEK for high temperature. And in aerospace, we are more on the right, with materials such as PPS, PEEK, PEC, low melt PAK, PEI, polysulfone. Those are the materials that you will see and find in aerospace. There is a niche in aerospace for polyamide, nylon. The F-28 was designed in the 1960s. It has magnesium steering wheels and magnesium supports for the pilot. Why? Because magnesium is very lightweight. But magnesium is also a dangerous material because if it catches fire, it burns. So today, designers are not very happy to use magnesium. And that's why when there was a new aircraft, next generation, this was in the 1990s, Fokker 100, the switch was made for the steering wheel and for the instrument support to go to polyamide as a polymeric material, and very successfully. So these steering wheels are a composite, short fiber composite. But what we discovered is that polyamide, if you have moisture and temperature, the properties drop dramatically. So for structures, we're not able to use polyamide on the structure part of the aircraft. So on the high end, there is a PEEK polymer. You may have heard of PEEK, very high performance material. It's been on the market since the 1980s. Today, there are more and more suppliers for this polymer, and it is used more and more. Then there is the PEI, the one on the specimen on your table, which is amorphous. So that's the only real limitation of this polymer, I would say. For the rest, it's excellent, in use since the early 90s, also in products on aircraft. And then PPS, polyphenylene sulfone. It's a polymer that is semi-crystalline, so it can handle all these aggressive fluids, but it does have a limitation in that the glass transition temperature is not very high. So for primary structure, it's not really good enough. So we have the PEEK for that, and then there's also the PEC, which is close to PEEK in processing temperature. And then today also there's a low melt PAEK, which has a little bit lower melt temperature than the PEEK and the PEC polymers. So it's a family of polymers. They are all high-end, as they say. They're not cheap, but they're technically very good. They can handle high temperature, high moisture content, can be used for primary structure on aircraft. And here's a bit of a description of different market segments. So at the top is the high-end, the aerospace, oil and gas, medical, defense. And if you go down into industrial, automotive, medical at the bottom, you see the polypropylene and the polyamide. And if you go up in the requirements, it's PPS, PEI, PEC, PEEK, low melt PAK. The material forms the fibers and the polymers together. So there are different forms. There is the material as one ply, so on a roll, a sort of a prepreg, and the prepreg can be used to make sheets. And so here's a sheet of glass thermoplastic. This is glass fabric with PPS, and I think this is about 4 plies have been put together under pressure in a press to make a very large sheet. And from the sheet, this has been cut, and this will become, after the processing, a product like this, a rib, stamp formed out of this. So it's either single ply material or a multiply plate type material. The single ply material can be laid up by hand or with robotics, automatic layup equipment, and the multiply material can be put into a machine like a press to be heated and formed into different shapes. And here's a picture from Toray Advanced Composites. These are 3 presses side by side into which you put the stacks of thermoplastic material, and then at high pressure and high temperature you make sheets. And these sheets in this case are 4 times 12 feet, 1.2 times 3.6 meters. And from these sheets you can cut all sorts of shapes, combine them nicely, and these shapes can be formed into parts.